Now we're going to look at a fundamental concept in inorganic chemistry, and that is the formula mass. So as a little bit of a review from one of the previous lessons, there was one value that we would find that was the mass of the atom, and that was our atomic mass. So remember, the atomic mass is a value that you can find on the periodic table. So if we look at our periodic table, that is the value that is at the bottom of underneath the chemical symbol. So for hydrogen, for example, it's this value there, the 1.008. So we have a similar value for entire molecules, and it has several names. It is known as the formula mass, molecular mass, and molecular weight. So for now, we're going to call it formula mass. And just like the atomic mass has units of AMU, atomic mass units, we're also going to use atomic mass units for our formula mass. And basically what this does is it combines the masses of all of the atoms in that molecule to find the total mass of the molecule. So for example, we have CO2, carbon dioxide, and we need to find the mass of the carbon and the mass of the amount of oxygen that are in this molecule. So if we go to our periodic table, and first we'll look at carbon. So here's carbon. So carbon has an atomic mass of 12.01. And then while we're over here, let's look at oxygen as well. Oxygen is 16.00. So we can go back to our problem. And we know that carbon has an atomic mass of, as we just said, 12.01. And there is one carbon atom in this molecule. So 12.01 times 1 is 12.01. Oxygen has an atomic mass of 16, and there are 2 of them in this molecule, CO2. So 1 for carbon, 2 for oxygen, and that gives us a total of 32.00 AMU. So when we total those together, we get a total sum of 44.01 AMU, and that is our formula mass for CO2. Now let's do the same thing for H2O. Hydrogen has an atomic mass of 1.008. You can look on the periodic table for that. And there are 2 of them. And that is going to give us an atomic mass of 2.016 AMU for hydrogen. And oxygen, as we've already looked up, is 16, and there is 1 oxygen in this molecule, so that is just 16.00. So when we add those together, we get 18.016. So notice our significant figures here. Notice that we have our hydrogen goes to the thousandths place. Now our oxygen only goes to the hundredths place. So we have to cut off our number there in the hundredths place, and that is going to cause our final answer to round to 18.02 AMU as the formula mass for H2O. So that's how you find the formula mass. There's another value that is similar and equally important, if not more so, and that is the molar mass. And the molar mass is essentially the same thing as the formula mass. The difference is the units. So the units of the molar mass are grams per mole. And we mentioned this briefly in a previous video. So that is the number of grams of a substance in 1 mole of that substance. And this is really key, because what this allows us to do is it allows us to convert between grams of a substance and the number of moles and therefore molecules of a substance. So let's do an example of that. Here's our example problem. If we have 10.8 grams of CO2, how many CO2 molecules do we have? So the best way to solve this is using the dimensional analysis that we have been working on so far this semester. So we know that we want to find the number of CO2 molecules. So that's the value, that's the number that should be in the top right box when you're finished setting up your dimensional analysis. The value that we are trying to cancel out is the grams. That's what we're starting with. That's what we're trying to get rid of. So that's where we want to start. So to start this problem, we have 10.8 grams of CO2, and I always write what the chemical is when we're doing our conversion problems, because if we end up, right now it doesn't really matter, but later on when we start working with chemical reactions, we're going to have multiple different molecules in the same problem, and it's going to be much easier if you write the molecule name in the box when you're doing your dimensional analysis. So we want to get from grams to molecules. Well, we don't know how much a single molecule, or we don't know how many molecules there are per gram of CO2. But what we do know is we know the number of molecules per mole of CO2, because the number of molecules per mole of anything is 6.022 times 10 to the 23rd. So it's that number of molecules per 1 mole. And again, it doesn't matter the identity of the substance. That relationship, the 6.022 times 10 to the 23rd to 1, that is always going to be a consistent relationship when using moles and molecules. So what we can do is, because we know the molar mass of CO2, we can get from grams to moles. We want grams of CO2 on the bottom because we want to get rid of it. So first we're going to convert to moles of CO2. And for every 1 mole of CO2, there's some number of grams. And we calculated this up here. Remember that the molar mass is the same as the formula mass, but with different units. So our molar mass of CO2 is 44.01. So 44.01 grams of CO2 per mole of CO2. And now we want to cancel out moles of CO2. And we want to get to molecules. We know how to get to molecules, so we can put that on the top. And for every 1 mole of CO2, we get 6.022 times 10 to the 23rd molecules of CO2. So now we check, we cancel our units. Grams of CO2 cancels with grams of CO2. Moles of CO2 cancels with moles of CO2. And we end up with molecules of CO2, which is what we were trying to solve for in the first place. so chances are we probably set up our math correctly. So go ahead, pause your video here, and take a moment to solve the math, and I will put the answer on the screen so you can check your work. So after you solve this problem, you should get 1.48 times 10 to the 23rd CO2 molecules. And notice we're rounding to 3 significant figures because out of our measured values, this one has the fewest number of significant figures. Notice we don't count the ones because those are exact values. Let's do one more example problem. An aspirin tablet contains 325 milligrams of C9H8O4. How many C9H8O4 molecules does it have? So for this problem, this one's a little bit more complicated because we have a slightly more complicated molecule. Notice how it also gives us milligrams to start instead of grams, which means that we're going to have to do another unit conversion. So let's plan out our problem to start. We know we're going to want to find number of C9H8O4 molecules. And in order to find that number of molecules, we can't go straight from milligrams or grams. We're going to have to figure out the moles. Once we have moles, we can use the molar mass to find grams. So let's add that in because that's an extra step. And we can find grams because we're given milligrams. So basically what I did here is I kind of worked backwards from where we're trying to get to back to the beginning. So the way we're actually going to solve this problem is to flip it around and to go from milligrams to grams, grams to moles, and then moles to molecules. So let's do that. We're going to start with 325 milligrams of C9H8O4. We know we want the milligrams to cancel. Milligrams of C9H8O4, and again, I'm writing out the whole molecule in my box. And we're trying to get to grams of C9H8O4. So now you want to ask yourself, how many milligrams are in a gram? There's 1,000 milligrams in 1 gram. And now we're at grams, so grams of C9H8O4. And according to our plan, we want to get to moles using the molar mass. So we don't have the molar mass. The problem didn't give it to us. But we can find it because we know how to find the molar mass. So let's do that. We know that we have carbon. We've already seen that carbon equals 12.01 grams per mole. And there are 9 of them in this molecule. For hydrogen, I'm going to just abbreviate this as 1.01. And there are 8 of them. Oxygen, we have 16.00, and there are 4 oxygen atoms in this molecule. So you can solve those on your own and fill them in. And it should give you 108.09 grams per mole of carbon, 8.08 grams per mole of hydrogen, and 64.00 grams per mole of oxygen. And we're keeping all of our sig figs because the 9, the 8, and the 4 are exact numbers. They're not measured values. There is no uncertainty there. We know that because we have a molecule, and we know we can't have a fraction of an atom in a molecule. We know that if it says that there are 9 carbon atoms, there's got to be 9. There is no uncertainty. So because there's no uncertainty, we don't have to count significant figures for those values. So we can total those together to get 180.17 grams over moles. So now we have our molar mass. We can fill that in. 180.17 grams per 1 mole of C9H8O4. And once we get to moles, we know we can get to molecules because we know Avogadro's number. Because we know that 1 mole of C9H8O4 is equal to 6.022 times 10 to the 23rd molecules. And I ran out of space, but that is molecules of C9H8O4. So go ahead and pause the video, solve the math on your own. So the answer you should get for this is 1.09 times 10 to the 21st power molecules of C9H8O4. And that's how you use molar mass in calculations.